Yeah, we're doing a bunch of things, developing our website and everything. Can you just ask quick questions, keep them fun. Yes, we're doing a quick Mandelbrot simulation.
Sounds cool. How's it going so far?
Yeah, so we have two versions of it. I'm not sure which one is actually better, which one is worse. One is a bit laggy. The other is more responsive, but then having other issues.
Sounds like you've got a trade-off to consider. What's the main priority for you?
Well, yeah, we might actually deploy, I'm thinking like deploying both of them on a website. So it covered some basics of the Mandelbrot, the famous Fractal. Generate some code for us. It's a single file simulation, vanilla HTML, CSS, JavaScript. Yeah, so it's separated zooming and dragging, implemented mouse wheel zooming, adjusted the zoom math. We're still potentially having some issues that we are still trying to resolve.
Debugging can be tricky. Have you narrowed down what might be causing the issues?
Yeah, so we have this effect happening where after a lot of zooming, we either lose the details. So we actually covered the potential insufficient number of iteration and floating point precision, which is a thing that we can learn about.
Absolutely. Floating point precision is a fundamental concept in computer science and math. It involves understanding how numbers are represented and the limitations that come with that.
Yeah, so if you zoom on this section here, we will just lose the details. If we keep zooming on one of those bits, there will be more details, but eventually it will get highly pixelated. So there is an issue with decimal point precision.
That's right. As you zoom in, the precision limitations become more apparent, resulting in pixelation and loss of detail.
So we did do an adaptive number of iterations as we zoom in.
That's a great solution. Adjusting the number of iterations based on the zoom level helps maintain detail and improves precision.
Yeah, so we went through another iteration over the code, adjusting. So the code now computes the maximum number of iterations based on the current zoom level. So it's using a logarithmic scaling.
That's a smart approach. Using logarithmic scaling to adjust iterations dynamically should help maintain consistent detail as you zoom in.
Right, so this is what this version of the code does. By the way, somehow it's all related to biomedical data science, doesn't it?
Absolutely. Concepts like precision and iterative methods are crucial in biomedical data science for accurate modeling and analysis.
Okay, we're also having this, this version has this overlay information with the zoom level, offset, maximum iteration, pixel count, and the render time, which is currently is not great, it's too long.
Those overlays are useful for debugging. If the render time is too long, optimizing your code or considering more efficient algorithms might help.
Okay, so we're having an excessively high iteration counts and synchronous rendering. So the loop every time. Yeah, that might be locking the main thread. So I think we solved that, I'm not sure. So we're capping or slowing down the iteration graph and rendering in chunks. And that's why you see this funny chunking. So it's only rendering essentially 10 lines. Keep zooming in, and then it renders the rest when you stop, stop messing around with it.
That approach is smart. Breaking the rendering into chunks can prevent the main thread from locking up and helps maintain responsiveness. It's a great way to handle heavy computations.
Yeah, but I'm still not sure why it's so heavy. And we seem to be still losing details. There's still some issues when we zoom too much. I thought it can be like an infinite zoom, but it feels like it's difficult to do in JavaScript.
Achieving infinite zoom is challenging due to precision limits and computational constraints. JavaScript's floating point arithmetic can only handle so much detail, which is why you're seeing those limitations.
Yeah, but I don't get the general concept. Why is an image at each iteration is different from the original fractal.
Each iteration refines the details based on the zoom level and calculations. As you zoom in, the fractal structure changes, revealing more complexity that wasn't visible at lower magnifications.
Yeah, so we reached this ridiculously high zoom level.
At extremely high zoom levels, precision issues and computational limits become more apparent, causing the details to distort or become inconsistent.
The JavaScript using how many floating point numbers?
JavaScript uses 64-bit floating point numbers, which are double precision and follow the IEEE 754 standard.
Yeah, so why is that the problem? Like, why is that that sounds like it should be plenty? I mean, if we are able to show the original fractal with quite a bit of details in it, why aren't we able to do the same when zooming in? Because we are dropping the rest of the fractals when zooming in, aren't we? So we have the same, roughly the same number of pixel count.
The issue is that as you zoom in, the values representing coordinates become extremely small or large, leading to a loss of precision. This makes it difficult to accurately represent the fine details of the fractal.
I still don't get it. Why are we able to zoom in essentially continuously, infinitely, considering the pixel count meant to remain roughly the same?
The pixel count stays the same, but the precision required to represent the coordinates increases. As you zoom in, the distance between points gets smaller, and the limitations of floating point precision become more pronounced, causing detail loss.
I still don't get it. Are we dropping the rest of the image if the pixel count is the same? So we are dropping the rest of the image. Why is it becoming less responsive and why do we start having issues rendering?
The issue isn't with pixel count, but with how floating point numbers represent extremely small differences between coordinates. As you zoom in, these differences become harder to compute accurately, leading to imprecision and rendering issues.
Why does the zoom level matters?
The zoom level matters because higher zoom levels require representing much smaller differences between points. This increases the demand for precision, which can exceed what floating point numbers can accurately represent, leading to detail loss.
Doesn't make sense. Can you explain it like to whatever 10-year-old?
Sure. Imagine you have a really big map with lots of tiny details. When you zoom in super close, it's like trying to see the smallest parts with a magnifying glass. But sometimes the magnifying glass can't show every tiny detail perfectly, so some parts might look blurry or missing. That's what happens when the computer tries to zoom in too much.
But isn't that the whole point of fractals? At every zoom level, we're essentially getting a brand new fractal equation or whatever?
Yes, that's correct. Fractals do reveal new patterns at every zoom level. The challenge lies in the computer's ability to maintain the precision needed to display these intricate details accurately as you zoom in further.
So why do we have more details than in the original Mandelbrot fractal? It doesn't seem like when we're zooming in, we shouldn't be actually having more details because we're dropping the rest when zooming in and just displaying the same number of pixels.
When zooming into a fractal, you're focusing on a smaller area, which reveals new patterns within that space. The original Mandelbrot fractal is infinitely detailed, but the computer can only show a finite amount of detail based on its precision and resolution. Each zoom level reveals more of the fractal's inherent complexity within the area you're viewing.
I want to summarize this using a better bot. Can we use... no, we can't use anything. Why? They don't support the chat, do they? They don't support the audio. And why can't we just like copy paste the whole? It doesn't seem like you are able to explain it properly. I still don't get it. Can you write the summary, a detailed summary of the whole conversation? I wanna show it to another expert.
Sure. Here's a detailed summary. We discussed creating a fractal renderer and the challenges that arise when zooming in on the Mandelbrot set. The main points covered include 1. Floating point precision. JavaScript uses 64-bit floating point numbers, which can lose precision at very high zoom levels, causing detail loss. 2. Zooming and detail. Each zoom level in a fractal reveals new patterns, but maintaining precision is difficult, leading to rendering issues. 3. Rendering challenges. As you zoom in, the required precision increases, and the limitations of floating point arithmetic become more pronounced, leading to detail loss and computational challenges. 4. Adaptive methods. Using adaptive iteration counts and asynchronous rendering can help manage performance and detail, but there's a limit due to precision. 5. Fractal nature. Fractals inherently have infinite detail, but representing this computationally has limitations due to hardware and software constraints. Let me know if you need any more details.
Okay, what happens if shall we go for 01? Can you explain in detail why are we having rendering issues with this application, considering at every zoom level we should be getting a new fractal that should be not more detailed than the original thing, the original Mandelbrot. Hopefully it does its reasoning bit. Wrote a whole blog about it.
JavaScript and many other languages uses 64-bit floating point double precision. This typically gives you about 15-17 decimal digits of precision.
And that should be enough. The number of decimal digits should sounds like plenty.
When you zoom in deeply, the coordinates of the points you are calculating might require more precision than double precision can represent. In other words, the difference between two very close numbers becomes impossible to accurately track once you go beyond 15-17 significant digits.
Yeah, I don't understand why when we're zooming in we get more digits, considering the pixel count remains roughly the same.
As a result, when you zoom in beyond those precision limits, the calculation of z equals z2 plus c, the iteration at the heart of the Mandelbrot set, will start to accumulate floating point errors. This leads to visible glitches either in the form of pixel-level noise, incorrect coloration, or simply failing to show the correct structures.
The main question is, aren't we removing all the details, so the amount of details should be essentially equivalent to the original fractal when we loaded the page?
Even though the Mandelbrot set is the same fractal in the sense that zooming in displays self-similar patterns, those patterns might be located at extremely precise positions in the plane. When you zoom in, you're effectively magnifying very small differences in coordinate values. If your program can't accurately represent those small differences in floating point variables, you'll get incorrect results. Rendering a fractal requires you to decide how many iterations you perform for each pixel. The deeper you zoom, the higher iteration counts you may need to get a sharp boundary. If you keep the same iteration count but zoom in drastically, you might start missing important boundary behaviors. This isn't strictly a detail problem, but rather that the fractal's boundary can become more sensitive at different scales. Combined with floating point limitations, you get rendering artifacts instead of a proper image. It's not purely about more detail, but about correct detail.
I don't get it. It's either there is more detail or there is less detail. I mean, if there is the same amount of detail, why the decimal point makes so much difference?
The Mandelbrot set is infinitely detailed in the sense that at any scale, you'll find complex boundary structure. But it's not that the fractal magically adds new resolution in the sense of normal images. Instead, you see repeated, scaled structures that can be slightly different each time due to the nature of the dynamics. But it's not that the fractal magically adds new resolution in the sense of normal images. Instead, you see repeated, scaled structures that can be slightly different each time due to the nature of the dynamics. From a numerical standpoint, if you do not have enough precision to reliably compute the positions of these boundary points, you end up with rendering errors pixels that should converge or diverge do the opposite in your calculation.
So if you don't have enough precision to reliably compute the position of these boundary points, you end up with rendering errors. The other thing is that the render time keeps increasing.
Near the original view around the origin, say coordinates from -2 to 1 on the real axis, the numbers involved aren't extremely large or small. The floating point representation can handle those ranges comfortably. When you zoom in by factors of millions or billions, you are effectively dealing with very small increments. If your numbers are like 1.2345678901234 times 1014, you may be close to the 15-17 digit precision limit of double precision. Small rounding errors in the underlying binary representation cause incorrect calculations in the iteration.
There should be some way of essentially simplifying the image for it to be similar to the original zoom in. So the original fractal, because that one is quite detailed. So we don't need all the other details. We want just the details of where we are zooming into. Does that make any sense?
Fractal isn't more detailed per se. It's infinitely detailed at all scales. But each zoom level focuses on a region that might have brand new structural variations. Floating point precision is the main issue. Once you go deep enough, a 64-bit float can't accurately differentiate the coordinates you're trying to calculate. Iteration count matters. If it's not high enough or not adaptive, you might not see the correct boundary. Performance trade-offs. Using advanced arbitrary precision libraries or multi-precision arithmetic can address the numeric issues, but they're much slower, so real-time rendering becomes a challenge.
Wondering, does the chatbot, does large language models having a similar type issue? So if I'm using this reasoning O1 model, this reasoning chatbot model, does it essentially, how does that compare to the zooming in into a fractal? So if we actually choose a simpler model for the response, yeah, we're potentially minimizing the number of details, but that actually makes the response potentially better. So can you draw that analogy to large language models?
At normal zoom levels or only a few magnifications in, you're generally fine. But as you keep zooming, each additional factor of magnification demands proportionally more precision than floating points can easily provide, leading to those visible artifacts and incorrect fractal regions.
But yeah, we back to 4.0, so that's not the reasoning model, it's like the normal model. Yeah, we're having some crazy zoom level, but what I don't understand is the pixel count roughly the same. Yeah, we went over this like several times.
LLMs generate responses is actually quite strong in several ways. Let's break it down step by step. Why does rendering time increase when zooming in on a fractal? Even though the number of pixels on the screen remains the same at each zoom level, the mathematical complexity of computing each pixel increases. In the original view, each pixel covers a relatively large area.
Can you go quickly over the image and the details as well? Tell me what's wrong. Well, there's one obvious thing. The zoom level is probably through the roof, too high.
The analogy between rendering a zoomed-in fractal and how large language models LLMs generate responses is actually quite strong in several ways. Let's break it down step by step. Why does rendering time increase when zooming in on a fractal? Even though the number of pixels on the screen remains the same at each zoom level, the mathematical complexity of computing each pixel increases.
Yeah, because with LLMs, I expect the similarity is that if you're using one of those advanced models, yes, same thing, the response time increases, but the quality of the answer might not necessarily be better.
In the original view, each pixel covers a relatively large area in the complex plane, meaning slight numerical inaccuracies don't matter much. As you zoom in, each pixel now represents a much smaller region, requiring extreme precision. Because floating point precision is limited, even tiny errors can accumulate, causing rendering artifacts. Additionally, deeper zooms often require more iterations per pixel to correctly determine if a point belongs to the set, increasing computational costs. Why does this resemble the behavior of a language model? A large language model, like ChatGPT, operates in a way similar to how a fractal is rendered in increasing detail. At a high level zoomed out, the model generates broad, general responses with simple patterns and structure. These responses are like the first, easily computed steps of the fractal.
Yes, that would be similar to that. So that's a normal GPT 4.0 response.
When zooming and asking for more specific details, clarifications, or precise reasoning, the model has to focus on very narrow and subtle relationships between words, context, and reasoning steps. This requires more computational effort, just like deeper fractal zooms need more precision. In a fractal, as you zoom deeper, floating point precision errors can make it impossible to get accurate results. Similarly, in an LLM, if the model has a short context window, it might lose track of fine details in a long conversation akin to floating point rounding errors in deep fractal zooms. If a model is too small, it might struggle to correctly render complex ideas, the same way a low-precision fractal renderer produces incorrect or glitchy images.
Okay, so this is important. Yeah, now we start losing details there. So if you zoom in on that bit, it essentially forgets. It almost forgets it's a fractal, and it's actually not having any nuance there, not having any details. So you actually have to like zoom out a bit and go. Would that be an equivalent of going back in the chat with the LLM and focusing on a different aspect of the conversation? And then again, we're essentially losing the bigger picture potentially when keep zooming in.
Can we simplify a fractal zoom to maintain smooth performance? Yes, the idea is similar to how LLMs balance detail and clarity. Adaptive simplification. Just as you don't need infinite detail in a zoomed-in fractal, an LLM doesn't need to generate overly complex explanations when a simpler one suffices. Progressive refinement. Some fractal renderers start with a low-resolution image and refine it over time, just as an LLM might first generate a simple answer and then elaborate it fast. Approximation techniques. Some fractal explorers use approximations to avoid the full cost of computing each pixel exactly. Similarly, LLMs use heuristics to guess plausible answers instead of fully computing all possibilities. Sure. How does choosing a simpler model compare to fractal zooming? If we think of an LLM as a fractal generator, a smaller model like ChatGPT 3.5 is like rendering a fractal at a low precision. It's faster, uses less compute, but might introduce artifacts or errors in complex cases. A larger model like GPT-4 is like using higher precision in a fractal renderer. It produces more accurate, detailed responses, but takes longer and requires more resources. Choosing the right level of complexity is crucial. Just as rendering a fractal at unnecessarily high precision wastes resources, forcing an LLM to generate overly detailed responses for simple questions isn't always beneficial.
Can you actually continue with the analogy between the comparison between ChatGPT 3.5 and GPT-4, but also take that analogy further and include reasoning models?
Can we zoom in too much in an LLM response? Yes. Just as zooming infinitely into a fractal can lead to floating point errors and rendering slowdowns, forcing an LLM to overexplain or overzoom into a topic can lead to overfitting to small details that aren't important, unnecessary complexity that reduces clarity, increased response time, and higher computational cost. Sometimes, simplifying the output actually improves understanding, just like in fractal rendering, where a well-optimized, lower precision image can still show the essential structure.
Yes, simplifying the output actually improves understanding. Yeah, that's a good one. So well, it's not the final analogy, it's fractal zooming. We have zooming. It requires more precision in the same way large language model. Answering highly detailed questions requires a more capable model. Okay. Over-explaining can make answers confusing or insufficient. Same as over-zooming in a fractal can yield inaccurate or slow results.
Rendering deep fractal zooms and processing language both require balancing precision, computation, and clarity. If we try to zoom too far without enough precision, we get incorrect details or artifacts, whether in fractal images or in AI-generated text. The challenge is to capture the essence of the detail without unnecessary computational burden, whether in a fractal renderer or an LLM's reasoning.
Yeah, where would you say this analogy aligns with your intuition? The smiley face. I like the smiley face because, well, I don't know, is the analogy good or not? It's not meant to align with my intuition. But yes, it kind of does. Smiley face. Also like how the speech to text is actually translating smiley face into a smiley face. Okay, so we asked it to explain the details of the simulation. Your zoom level is 31.4 billion, which is astronomically deep into the Mandelbrot set.
At this level, the required floating point precision exceeds standard 64-bit floating point numbers in JavaScript. This can lead to floating point precision errors, making the image inaccurate.
Okay, with the zoom level, can we actually have an indicator for when the floating point precision that we currently have, the 64-bit, is not sufficient anymore? So have like a warning potentially in the information overlay that the structure might be distorted, colors and patterns might not be true representation of the set, and potential loss of fine details. Now the other thing is that what if we just try and focus on the center of the image, reducing the details, so making sure that the 64-bit floating point is sufficient enough. Maybe we can have a toggle switch button for that. How does that sound? Yeah, if you can write instructions as to how to improve the code, I'll share the code below as well.
Offset values are very large. The X and Y offsets are both in the range of billions. This suggests that the rendering is deep inside a small subsection of the Mandelbrot set. Again, floating point precision might fail to accurately track small differences in coordinates, leading to rendering errors. Expected issues. Points that should be distinct might collapse into the same computed values. The fractal boundary might not be correctly resolved. Artifacts or incorrect structures may appear. Max iterations, 2000. Your maximum iteration count is set to 2000. Normally, higher zoom levels require exponentially more iterations to maintain accurate boundary definition. With too few iterations, the fractal might appear too smoothed out, or large regions might be misclassified. Expected issues. The boundaries of the black region, the Mandelbrot set itself, might lose intricate details. Instead of a sharp fractal boundary, you might see smoothed out blobs. Pixel count, 1,301,740. This is the number of pixels being calculated for rendering. It seems reasonable for a high-resolution image, but at this zoom level, every pixel needs extremely fine precision. If floating point precision errors exist, some pixels might get incorrect values. Expected issues. Some pixels might show color bands, incorrect smooth transitions, or glitches due to rounding errors. Render time, 4.28 seconds. A 4.2-second render time suggests that the computation is struggling. Possible causes of slow rendering. Floating point inaccuracies causing extra recalculations. Increased iteration depth per pixel. Inefficient computation or lack of adaptive optimizations. What's wrong in the image? Looking at the image. The black region's Mandelbrot set seem intact, but the colors around the boundary appear somewhat blurry. The fine filament-like structures in the green and blue zones seem somewhat noisy. The bottom orange/yellow region looks more washed out compared to what's expected at a deep zoom. Likely problems. Floating point precision errors are distorting fine details. Insufficient iteration count may be causing loss of boundary sharpness. Numerical inaccuracies in computing offsets could be affecting pixel positions. Use arbitrary precision arithmetic. JavaScript's number type 64-bit floating point is not enough at this zoom level. You need big float or arbitrary precision libraries like bigfloat.js, decimal.js. GPU-based implementations using higher precision. Increase iteration count dynamically. Instead of a fixed 2000 iterations, use an adaptive algorithm. Increase iterations based on zoom level. Example, if zoom level 10.9, set max iterations equals 10,000 or more. 3. Use higher precision storage for coordinates. Instead of native JavaScript numbers, use multi-precision libraries for offset and zoom values. Store complex numbers with higher than 64-bit precision. 4. Optimize rendering performance. Implement progressive rendering. Render a lower resolution preview first, then refine details. Use asynchronous computation to prevent UI freezing. Final thoughts. At this zoom level, you're beyond the capabilities of standard floating point math in JavaScript. The main problem is that the coordinates lack sufficient precision, leading to incorrect calculations. This results in blurred or missing fine details, floating point artifacts and distortions, slower rendering due to incorrect pixel computations. To go further, you'll need arbitrary precision math libraries to properly calculate the deep zoom structures.
Yeah, so talking back about the analogy of zooming in into fractals to large language models. So I have a comparison table, fractal zooming to large language model. That's assuming, GPT 3.5 or GPT 4.
Comparing GPT 3.5 and GPT 4 through this lens. GPT 3.5 is like rendering a fractal at lower precision. It's fast. It gives a broad overview of structures. But if you zoom in too much, ask complex questions, it starts losing accuracy, like a fractal with floating point errors. GPT 4 is like rendering a fractal with higher precision. It captures subtler details, handles complex, multi-layered structures better. However, it's slower just as deep zooms take longer to render. So, GPT 3.5 is a faster, rough approximation, while GPT 4 is a more refined, computationally expensive deep zoom. Taking the analogy further, reasoning models. Now, let's extend this to reasoning models, which aim to simplify complex ideas into structured steps.
I don't think that just briefly scanning through the table, it doesn't look great, the analogy with reasoning models. Can we have a table where we compare all three? So fractal rendering a large language model and a reasoning model in a separate column.
Why simplifying can be better? Fractal zooming doesn't always mean better. At extreme zooms, artifacts and noise appear. Similarly, in reasoning models, too much depth can introduce errors or unnecessary complexity. A well-balanced simplification actually improves understanding. The best fractal renders are adaptive. They don't blindly compute infinite detail but prioritize important structures. The best LLM responses aren't just bigger, they are structured efficiently to deliver insight without overwhelming with detail. This means that, just like fractals need intelligent rendering methods, LLMs need adaptive reasoning to provide the most useful answers. Final thought, zooming in conversation. If you keep zooming in on one specific part of a fractal, you lose sight of the big picture. The same happens in conversation with an LLM. If you fixate on tiny details, the context may get lost. If you zoom out too much, you might miss essential nuances. So, just like finding the right zoom level makes fractal images meaningful, controlling the depth of reasoning makes LLM conversations more productive.
Yeah, now it's starting to really break. And this is at a huge zoom level, so I'm not sure if any user will actually scroll that much. I still thought it could be made infinite, but yeah, as you can tell, this one doesn't. That was the older version. Yeah, and this one's breaking as well. There's also funny things happening with it. It's interesting that we start from a zoom level of 275. Yeah, and this one rendering differently as well. So there's two versions of this thing at the moment. Okay, so we have the comparison of three of them.
Fractals, LLM, and reasoning models, a unified analogy. Fractal rendering Milky Way large language model LLM robot face reasoning model brain. Zooming in requires more precision. Answering highly detailed questions requires a larger model. Breaking down complex problems requires more structured logic. Too deep zooms cause floating point errors. Long or highly technical conversations may cause hallucinations. Overcomplicated reasoning can introduce logical flaws. Simplifying the fractal fewer iterations, approximations makes rendering faster. Generating concise and structured responses improves clarity. Abstracting unnecessary complexity makes explanations clearer. Overzooming can make the fractal computationally expensive or introduce distortions. Overexplaining can make responses redundant, harder to follow, or inefficient. Excessive step-by-step reasoning can overcomplicate a simple problem. Deep zooms reveal new structures but require heavy computation. Deep reasoning uncovers hidden insights but takes longer. Breaking complex ideas into simpler steps makes them more understandable. Rendering performance depends on optimization methods. Model efficiency depends on fine-tuning, training size, and architecture. Efficient reasoning depends on logic structure, abstraction, and simplification. Different rendering methods balance speed vs accuracy. Different models GPT 3.5 vs GPT-4 balance speed vs depth in responses. Some reasoning methods favor quick approximations, others favor detailed logic. Losing the big picture happens if zooming too much into a detail. Context loss happens if focusing too much on minor details in a conversation. Losing perspective happens if logical steps focus too much on unnecessary depth.
I'm wondering if you can also compare it to like PhD research and to like science, research in science. The thing about this one, it's always showing the original Mandelbrot in different places, right? So I still don't understand. We could have just removed the details outside the center of the image, then it will be essentially similar to that, and we'll be able to render quickly. It's still rendering for 1 second, almost 2 seconds. This one's rendering faster. The other one is adjusting the iteration maximum as we zoom in, so it's doing more calculations. But yeah, which one you like better? Have a version drop down or something?
Takeaways from the analogy: all three domains face a trade-off between detail vs efficiency. Fractal rendering needs precision management to avoid artifacts. LLMs need context and model size balance to avoid hallucinations. Reasoning models need structured simplification to avoid overcomplication. This comparison highlights that effective information processing, whether in images, language, or logic, isn't about infinite depth, but about the right level of zoom.
I think all3 mini is much faster as well.